Yeah, I'm Fergal Walsh. I work at Hippo. We're a product consultancy based in Istanbul and Toronto with remote people around the world. And so today I'm talking about building a fine-grained image classification system for nature images. So your first question is, why would you want to do this? Well, one of our long-running client projects at Hippo is a project called Fieldguide. And this project has the modest goal of being the field guide for everything, literally everything. So by a field guide, they mean a visual catalogue and encyclopedia of things to help people to identify and to find out more information about those things. So initially we began as a field guide for all sorts of everything, but we narrowed down our focus to just nature, to tackle a kind of an easy problem to start with. So just a brief overview of what Fieldguide is. So it's a website and it's an app, and it has a large hierarchical category system. So here you can see a lot of different families of moths, which are under the category of butterflies and moths, under insects, etc. And then you can dive down deeper into specific families and then into individual species of moths, and you can see the kind of encyclopedia information about them and their geographic distribution, etc. And then it's not just moths, it's also mollusks and birds and plants and basically every kind of animal you can think of. But obviously with a bias towards animals and biological organisms that are interesting to photograph and collect. So where does image classification come into this? Well, the way that this catalogue gets populated is that people upload images. And then they wait a second, and then the system tells them what their image probably is. And then they click on it, and they compare it to the existing images that are there. They check the geographic distribution if it matches, and then they add it to the collection with some extra fields, and then it gets added to their profile and to all the existing images in that category. So this talk is about what happens while that little circle is spinning. It's a screenshot, so it's not spinning, but you get the idea. So the rest of the talk is about that. So briefly, I'll talk about what is image classification, why do we need it, and then most of the talk is about our computer vision journey in building this product. I'll talk about the technology, the challenges, our solutions, and the remaining open problems. So basically, the problem of image classification is the task of assigning a class label to an image. So if we look at these two images, we can easily say, well, the top one is a bird and the bottom one is a butterfly. But we can also go more detailed than that, and we can say, well, the top one's a swallow and the bottom one is in the family of the white type of butterflies. And then we could go even more detailed. So we want to know, is it an African swallow or a European swallow? It's important sometimes. Or the specific species of the butterflies. But when we're dealing with nature, we usually use a different system of classification, which is the taxonomy, which is this system of orders, families, families, subfamilies, tribes, subtribes, genus, and species. So that's what we see here. We see the family name, the genus name, and then the species name. So if you remember that we are the species of Homo sapiens, so that's the genus of Homo and the species of sapiens. So in traditional image classification, we would take our training images and then we'd feed them through some kind of feature extractor, which would measure things like the color histogram, find key points in the image, distributions of geometrical shapes or edges, these kind of things, and then encode them into a numerical vector. And then we would train a classifier to basically find the find the line, basically, that separates the classes in our system. So in this example, we have two different types of data points, and we have the line that separates the two of them. So that's the basic idea of traditional image classification. Train the data, feature extraction, classifier. So that's what we began with when we started this project. We started researching these kind of methods. That's what we were familiar with. But then we came across this demo. This was quite a few years ago, by the way, where they had this website where you could just upload images, and it would give you back reasonably good descriptions of what those, or categories of what those labels for what those images might be. And the interesting thing about this was that there was no feature extraction step in the process. It was just upload your image, and it converted it into categories. So we looked further into this, and this is this is part of deep learning and convolutional neural networks. I'm not going to explain this diagram, but basically the important thing to note is that it contains all of the feature extraction and classification inside one neural network. So an image goes through one side, and at the other side comes probabilities of different classes. Now, why this is interesting is not because we were going to go and build our own neural network, but there's a challenge data set called ImageNet, which is a database of over 14 million images in 20,000 different categories. And this is a data set that's been built by academics for benchmarking image classification techniques. And the nice thing is that the academic community in this area, when they benchmark their models on this data set, they also publish the model so that other people can verify it and other people can reuse it. But they don't just publish the architecture as a paper or as a diagram, they publish the actual trained model. And because this neural network has been trained on this ImageNet dataset, so it's on a subset, it's not 20,000 categories, but it's a subset of 1,000 categories that they use for the competition, then you can basically take this already trained neural network and use it for classifying your own images. So this is exactly what we started with. It's not always correct. That's not a butterfly, that's actually a moth. And there's a difference. So our very first system was to package up that demo application, which is written, it's made using the Caffe deep learning framework, which is basically for training deep neural networks and using them. And it has a Python API. So we just fed a query image through that network. We treated it as a complete black box. We did not care about what goes on in the middle. The only important part was what comes out at the bottom, which is the classes in terms of ImageNet. And then we just mapped those classes to the classes in our system. And this was great because, well, it enabled us to do some nice demos to show to potential users of this app about how we could quickly classify your images into all sorts of different categories. It was fast, and it could help us on the step of building this catalog. But will it be able to learn? Can we teach it about moths or shells? So, for example, it knew about butterflies, but it didn't know about moths. But say if we have a lot of moth images, can we teach it about moths? Or some new category like shells? And unfortunately, no. We can't incrementally train this classifier. But could we, say, retrain the whole thing from scratch on a regular basis as we add new images? And again, the answer was basically no, we couldn't, because it would take a few weeks of GPU time to train it from scratch, and you would need to have millions of training images. And obviously, as you're building your system at the start, you don't have millions of training images. So then we looked at alternative ways of how can we actually take this classifier and make it more useful for our purposes? Can we actually make it learn new stuff? So then we thought, can we reframe this as a search problem instead of a classification problem? So what this means is, can we search for the most similar images in our database and then use the categories for those images as suggestions to the user. And we followed we took inspiration from a paper published by Pinterest and a few other similar papers at the time. And what they did was they took this convolutional neural network and they stopped treating it as a black box. They looked inside it. And what they realized was that basically the very last layer before the classification layer is a really, really good feature detection layer. And what it outputs, instead of the probabilities of 1,000 classes, it outputs a vector of 4,096 dimensions, which is just a big long list of numbers. But those numbers represent something about the features in those images. So what we did was computed and stored the feature vectors for all those images, all the images that we had. And then at query time, we compute the vector for the input image, and we compare that to all the existing vectors and find the most similar ones, and then use those to suggest the classes. And calculating the distance between these vectors is the same thing as calculating the distance between a vector or 2 points. So 2 points in 2D space is just a 2D vector. Two numbers is a 1D vector. So these were 4,096 dimensional vectors, but it's still just Euclidean distance between them. So we put all of those into a big NumPy array. And then when a query image came true, we converted it into the vector with the Caffe network. And then we did a Euclidean distance across the NumPy array, and then we found the most similar images, and then we used those to find the categories to suggest to the users. And it was great. It was fast. Sometimes it worked like magic. And the new images were immediately indexed. So if I upload a new image, an image of some species of moth or butterfly or something, and then soon after I upload another image of the same species, well then it will likely suggest that same species again, because it can immediately just find the most similar image in the database. So it doesn't have to be periodically retrained. It's constantly learning to some extent. But keeping that big NumPy array in memory wasn't so sensible. Memory usage grew over time, and query time grew linearly with the number of images. And then sometimes it just seemed like it learned nothing at all, which was really frustrating, because sometimes it's great, and then you try a different image, and then which looks relatively similar, and it just was totally wrong. And the main two problems were that the system, didn't know where to look, so it didn't differentiate between the subject and the background of images. So often it was giving suggestions where the background of the image were very, very similar to each other. So say two different species of animals that were photographed in long grass or on a flower or something, but the actual animals themselves were totally different. And to us it was like, what is it doing? This is just stupid. But to it was perfectly reasonable. Most of the image is basically the same. It's the same colors, same kind of shapes. So, because it wasn't trained to know anything about the actual objects. And then it was very sensitive to different sizes and different rotations of images, which was annoying. So our two solutions to those problems were we moved to Postgres instead of that big NumPy array. So we put all of our vectors into Postgres. We used the cube extension in Postgres to do Euclidean distance search. But that was pretty slow as the Postgres, or as the number of vectors increased. So then we added a second table of binary hashes of the vectors. And then we used a extension module called PG similarity, which implements the Hamming distance, which is just a very, very fast way of computing the distance between two binary arrays. So we used that to filter down to, say, the closest 1,000, and then within that we did the slower Euclidean distance. And then we started looking into image segmentation techniques. So can we automatically separate the subject from the background? And we came across this amazing technique called grab cut, which does this. You draw a bounding box around the object in your image, and it can just be a tiny, so in this image we just like made the bounding box a tiny bit smaller than the actual image. And it uses the information of what's outside the bounding box and what's inside the bounding box to work out what is foreground and background. And then it gives you a mask, which then you apply to the image, and then you basically remove the background from the image. And this worked amazingly well a lot of the time. And the nice thing about this was then we could auto-crop the images. So even if like one image was zoomed out, one of them was zoomed in, then by cropping we made them all relatively similar sizes. So our kind of flow diagram changed from this into this. So our Numpy array gets replaced with Postgres, but other than that it's basically the same. And then we added in a auto crop and auto rotate step using that grab cut from OpenCV. So there's our second Python reference, by the way. And this was great. It was stable. We didn't have the same kind of memory problems. It was a lot more scalable. And it was less confused by the background patterns. So overall, it was good. But over time, of course, it got slower. And the autocrop was never perfect. So it was good, but it was frustrating because sometimes it would just do something wrong. So in this case, actually it's very reasonable from the algorithm's perspective because it picks out the leaf as the object in the image. But whereas what the user was interested in was the moth. And then as you do these kind of projects, the users or the clients are like, wow, this is absolutely amazing. We can classify all sorts of anything into categories. But they quickly get used to it, and they want more and more and more. And they expect, when they see it working well, sometimes they expect it to work all the time. So our solution, well, TensorFlow came out somewhere around that time. For a while we tried to ignore it and just focus on what we were doing, but it seemed like it might be pretty useful. So one of the few attractions of it were supposedly easy deployment. We could use it on clusters of servers and mobile, and it's basically a framework for deep learning. So we decided to try it. And there were some tutorials about a process called fine-tuning, which is an alternative to training a full network from scratch, but where instead you take an already trained network and you take out the classifier layer at the bottom and give it your own categories and fine-tune the weights. So leave most of the weights in the network as they are, but fine-tune the rest of the weights to make it actually work on your new problem domain. So we did this. We experimented with just butterflies and moths, Lepidoptera, which from now on I'll just call leps. And so we had about 3,000 classes with varying between 20 to 1,000 images per class. It took about 24 hours of GPU time to train. And in this case, we didn't do that image segmentation step anymore, which was a bit disappointing because it was so cool. But we thought that we don't need it because we're going to train the network and we're going to make it learn the difference between background and foreground, the things that are important, the things that are not. And in the end, it was pretty accurate, especially given those 3,000 classes. So our classifier was something like this. We took a query image straight through the inception network, which was the state of the art at that time, just another deep neural network. Again, we treat it as a black box. We get out some classes, and then we threshold those, and then we return some suggestions to the users. And then we ran this in parallel to our existing system, kind of merged them a little bit together, but we mostly had two separate systems running side by side, one using Caffe and one using TensorFlow. The reason we did this was because our new system was only trained on these LEPS classes, but we still wanted the other system to work for all the other different kinds of images in our system. And it was fast, it was accurate, and importantly, the accuracy was measurable. And this was a really useful thing because we kept getting asked, how accurate is your classifier? We had no idea because it changed all the time. It depended on what images were currently in the database, and if you add one new image, it could just totally destroy the accuracy for all sorts of classes. But in this case, we had a proper training setup where we had a training set, a validation set, and then a test set. So we could actually measure the accuracy across the whole network and then across different subsets of classes. So that was very nice. But this pure classification approach had one problem, which was that when we got rid of similarity ranking and just used classification, then so in the image on the right, on the left, you can see that the category cover image that it suggests is extremely similar to the query image. But in the one on the right, the image that's uploaded, it looks quite different from the cover image. And when you're uploading your picture, you're wondering, well, is it right or is it making a mistake? And I can't tell from that image because it looks entirely different. And then this is kind of a problem, aside from just that kind of example of different angles of, by the way, that's the exact same individual butterfly, by the way. It's just different size of their wings. But here's another species where all of these images are the same species. Because butterflies look entirely different when they're children versus when they're adults. And then when they're museum specimens, they have their wings spread like this. By the way, if you ever see a butterfly image like this, it's a dead butterfly. Living butterflies never look like this. Usually they're like this or like this one below. But all of these are quite different in terms of their colors, their shapes, their poses, everything about them. So we brought back the similarity ranking. So within the classification results, we then did a similarity search to try to find the most similar images. So our flow looked like this, and then it became this. Now the only advantage to this diagram is that it's slightly more symmetric. Other than that, it was basically a nightmare because we've got two kind of parallel systems which are similar enough to each other, but they're not the same. Even the vectors from this size are 496 dimensional. The ones on that side are 2048. And yeah, so there's even the database tables are not the same. But it solved the problem that we had, so that was good. So the results were much more useful because if I upload an image of the butterfly in this pose, well then I get back the suggested category cover image is in the same pose, which from a user experience perspective is a huge gain. So this makes it much, much easier for users to add images to the system. But there are now 2 neural net passes required, because one for classification, one for similarity, one for feature detection. I skipped over the bit on the previous slide was why we had to do that, but basically as we retrain the classifier net, then the feature layers are also changing slightly, to some small extent, but they're changing. And it means then that the vectors extracted from one net are not comparable with another net. And we didn't want to recompute the vectors for millions of images every time that we updated our classifier. So we just said, okay, fine, we'll keep one of them static and we'll retrain just the classifier net. So now we had 2 neural nets that we have to keep online, and then the images pass through them. It takes some time to pass through the neural net, so it adds latency. And then the main problem was that we had 2 parallel systems, which was just not a good idea. So the solution, we weren't ready yet to train a specialized classifier network for every single category in our system. Because we were still trying to be this really broad system, not just focusing on LEPs or on just on mollusks or these small categories, but just really working for all sorts of everything. So what we did then was we trained another neural network to classify into the broad nature categories that we were dealing with. So this is an insect, this is a mollusk. Mollusks are seashells, by the way, or sea kind of creatures. Most of the pictures are of shells. Plants, birds, fungi, bees, all these different kind of like high-level classes that we had. And then, so our new system was like this. So then this top-level classifier acted kind of as a router, and it either directed the request to go down to the LEP's inception classifier, or else it directed the request to go to the inception feature extractor and then the similarity search through the database. But the nice thing about this approach was that, again, we had one database, we had one framework, we have now got many neural networks to deal with, but still it's all under the same system. But the problem was that the users really liked it on the left side, and they wanted everything to work like that. Because some of these, so there's these whole community groups that are just fascinated by different types of animals, and one of them is LEPs. So there's these moths and butterflies photographer groups, and they're really into their LEPs photography. But they also then dabble in a bit of bird photography, or some of them are into plants as well, and so they're kind of they do a bit of nature photography in general. So they wanted to use the system for those kind of things, but they were used to the performance of the LEPs version. And then we were importing a lot of data. So in Fieldguide, we're working with a number of museums to some of them to actually digitize their collections. So if you go to any natural history museum, even in Dublin, there's these display cases where they have all these pinned specimens of different species. So some of these museums, they have thousands, tens of thousands of these actual pinned specimens. Some of them have already digitized those, and they have high quality images. Some of them have terrible quality images, and some of them don't have them digitized. So one thing we did early on was we released a specialized LEPs app, which allowed these museums to digitize their collections of moths and butterflies using an iPhone app, which was a great way of adding more training data to our system. So, yeah, we tried to think about how do we scale this to a wider set of categories. So we thought, well, can we just build a single neural network with, say, 100,000 classes? And unfortunately, no, seems to be the answer. Because all of these methods are benchmarked with data sets of about 1,000 classes. There's some other smaller or some other bigger data sets which go up to about 10,000 classes, but there's very little research on doing classification, fine-grained classification on larger numbers of classes. So then we thought, well, okay, we'll keep with this hierarchical approach. Maybe we'll just train many of these specialized inception nets. So one for fungi, one for birds, one for plants, one for LEPs, etc. But that seemed a bit ridiculous and costly. Because the problem with this is that as you have more classes, it takes longer and longer to train, and training requires GPUs. And GPU instances are expensive. And then at inference time, each of these networks takes up quite a lot of memory. So about 700 to 800 megabytes per net, and then each net can only predict across one image at a time. So as you scale out, that's an awful lot of RAM taken up. So we kind of took a step back and wondered if we were looking at this a bit wrong. Why do we think the solution to every problem is another neural net? Maybe because we're in this TensorFlow world, everything just looks like it should be solved with an inception. But maybe we could have gone back to that traditional approach where you split the feature extraction step from the classification step. Because in reality, most of what the neural network is doing is feature extraction. And it's just a small little classifier in the end. And a lot of the features in nature images are actually quite similar. So the types, like, you're not dealing with, or the types of shapes and the types of textures and things, they're similar across different classes of natural species. As opposed to, say, like man-made objects, which have very different kind of features, different colors, different shapes, different geometric features. So we thought, can we train one general purpose nature feature extractor, and then train a load of small, old-fashioned linear classifiers to work with those features? So, yeah, this was the inception architecture. Again, most of it is feature extraction, and then at the end is just this tiny classification layer. So we said, okay, let's just try to use this for feature extraction. So we trained it on about 5,000 different genus categories from across our category tree. So including moths and butterflies, but also mollusks, also plants, also birds, little bit of everything, to try to force it to learn the generic features. And then we trained, so using scikit-learn, we trained a lot of linear classifiers. A lot, I mean, like, I think about 2,500 separate classifiers to make a big kind of hierarchical ensemble of classifiers. So here you can see that the idea is that you go first through the inception feature extractor, you get a vector, and then you feed that into the nature classifier. It classifies into one of these high-level categories, and then it sends it, in this case, down into Leps classifier, which then sends it to the genus level classifier, and then within that genus level, it classifies down to species level. In this case, I just show one line, but it can also take like classes from a few different parts of the tree. It doesn't necessarily just get stuck down one path. And then, so we took our architecture and then modified a bit to fit this into it. So we replaced what was three different inception nets with one inception net and then this big hierarchical classifier. And then the same feature vector feeds into the similarity search. So we have this kind of hierarchical classification and the similarity search. And this was great because we didn't need to train any neural networks anymore. We said that, okay, we have our feature extractor, that's trained, let's just leave it as B. And now we're just going to train these small linear classifiers, which are much more lightweight than neural networks. And they're, easy compared to training neural networks. And then inference was very fast because there was only one neural network involved. And they used a fraction of the memory, so we could have so we have 2,500 different classifiers running on one instance using about the same amount of memory as a single inception net, because you can easily swap them in and out of RAM as well, whereas an inception net, if you swap them out, then you're going to have a huge delay every time you reload it. And it gave best effort hierarchical results. So that meant that sometimes it basically said, okay, I'm pretty sure this is this genus, but I don't know what it is beyond that, which was more useful than saying, I'm pretty sure it's this species, but it'd been wrong. So it actually, it kind of had an element of self-doubt in it, which was useful. So then we could say, okay, it's brought us down to genus level, then we will work out ourselves what is the species. But it didn't work. Well, it worked, but it didn't work as well as we hoped. The problem was that we were all used to the level of accuracy that we got in the specialized net, and we just didn't get it with this approach. And that was disappointing, because that diagram looked an awful lot nicer than the previous one. But the main problem was that this approach is much less robust to noise and mislabeled data. So what this means, noise is like where Well, mislabeled data is easy. Something is labeled as a butterfly, but it's actually like a fish. It's just something is in the wrong place in the category tree. And this happens a lot because we have something like 100,000 categories in our system. So it's quite hard to keep it all under control and in the right place. And then noise is where you have something that is supposedly some insect, like maybe a beetle, but all you can see in the picture is just plants, because the beetle is tiny and the plants take up all the rest of the image. Or you have like bird photographers who take images of like birds far, far in the distance, and most of the picture is the grass, the trees, the sky, and then a tiny little speck of a bird, which no human could classify, and there's no chance that the computer can classify this. So all of this noise is a problem, and it's much more of a problem in the training approach that we use on these small classifiers than it is on the inception net, which takes an awful lot more time to do its training. So we're still trying to get this to work better. We're working on manual and automatic curation. Manual is difficult because currently we have about 15 million images in our system, because we've imported images from all over the world, all over the internet, and all sorts of different collections. And some of them are good and some of them are terrible. But we have ideas on automatic curation of this, of basically feeding all of the images through the top level classifier. If it's meant to be a bird, but the top level classifier doesn't classify it as a bird, then it means that it's a garbage image. It means that there just is not a useful looking bird in that image. So then we disregard it. So we reduce our 15 million down to probably, 2 million. But it means that we can have much more accurate classifiers. And then we also hope to investigate object detection techniques so if we have a high resolution image of a bird in the sky, then maybe if we zoom in really closely on that bird, then we can actually find features that are useful. But to do that, we need to be able to work out where in the picture the bird actually is. So we still are hopeful that this approach will work. But for the time being, we've gone back to basically replacing some of them in the areas that we care most about with inception nets. So the solution to the problem is just more inception nets. Which is annoying because it's a pain to manage all those. It takes a long time to train them, and they use up a lot of RAM, and yeah, it's just not fun. So our overall system architecture looks something like this from a component perspective. So a CV request comes into the CV service, which is like a web service, and then it basically sends that down through the hierarchical classifier, which goes through the feature extractor service, which then returns the vector, gets classified, and then it might get then sent off to one of many inception nets for further classification. And then it uses the similarity module with the same feature vector to search across the database. And then that database is constantly being populated by this ingester, which is basically a process that just downloads all the new images from our platform and runs them through the feature extractor and then saves the vectors to the database. And most of these are implemented as separate different web services. So it's kind of like a microservice architecture. They're all, so this is Pycon, so yeah, these are all written in Python. The whole system is written in Python. Most of these are using TensorFlow and Numpy, scikit-learn, and then Pico is the web framework that we're using here, and we use a bit of Flask as well. So, some lessons and conclusions. This computer vision and machine learning research field is quite amazing, actually, because very differently from a lot of other academic fields, everything they do is really in the open. So, of course, they publish their papers, but they publish all of their code and all of their models, and you don't just have to take their word for it that what they're doing is correct. or that the results they claim are really true, you can download the model and you can run it and you can test it. And there's, yeah, so it's a very, very fast-moving field at the moment. The very best libraries and frameworks are all in Python, so TensorFlow, Caffe, Tiano, Keras, PyTorch, all of these, they have their top-level API in Python at least. One thing that we found out was that computer vision and classification starts out as quite plug and play. You treat everything as a black box, but you quickly end up down the rabbit hole. And once you go in down so far, then you just keep on going. Because you put so much effort into it, you just want to get it to work. There's an awful lot of custom code required. So you have all these frameworks and libraries, but you write a huge amount of pipeline code and glue code to just to process your raw images and to move them around the place, saving different intermediate representations of them. It's something that you don't think of, and you think that, okay, I can just download a whole image classification system and just run it, but no, there's a lot of other code that you wouldn't think of that's involved. And then the main lesson is that scaling CV is hard and expensive. So Google is really annoying because they keep coming out with these amazing demos of things that they can do. So for example, we have this Google Lens app where you just point it at, you take a picture of things and it tells you what it is. And people are really impressed by that. And it is really impressive. But we don't know like how many classes of things they're classifying, how they do it, but they have near infinite resources. They can afford to run many, 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 many different inception models, inception-like models, on GPUs in their cloud, and they're not really bothered by the cost of it. But when you want to do it as a small startup, or as a non-profit, as in this case, then it doesn't make sense. You can't do that. You can't be paying for multiple GPU instances to be running constantly. Doesn't make sense. So then, yeah, you can't have the same sort of speed and you can't have the same sort of design. So while there's a lot to learn from the likes of Google and Facebook in these kinds of things, there's different approaches that you have to take as a smaller team and a smaller company. And then, yeah, neural net orchestration is kind of a thing now. So we need something like Kubernetes for neural nets at this stage. When you have a load of them and you need to constantly retrain, update, make sure you have enough instances of them running to keep up demand in that particular part of the category tree. And then unfortunately it still needs a lot of human supervision and manual intervention. So I've tried to automate a lot of this, but there's still, even trying to work out when to stop the training of a neural net is a bit problematic. And so most of the time we just let it train for a few days or a week or more, watch the metrics, and then as they reach a certain point, then we stop. But when we automate this, it just goes wrong. It's one of those things that humans are still much better at than machines. And then the other brief thing is that you're all here and you're not in the talk next door. So next door they're talking about metrics and logging and things. And one of the things that I found immensely useful was to basically log every single request that comes into the CV service, and with the image, with the source, with what device it came from, but then also to keep the application logs, so the Python logging messages. So then you can output some messages as you're going through the different processes. And then if you collect all of these logs, even if they're running in separate processes under different web services, if you collect them all together and display them all together for the same CV request, and if you keep them all in the database, then it makes it super easy to debug things. So yeah, logging is important. That's it. Thank you.
was a wonderful session. Thank you.
Thank you.
I think years of